Hello students, this video lecture will cover section 11.7, areas and volumes of similar solids. Our learning goal for today will be able to compare and find the areas and volumes of similar solids. So let's start with some vocabulary. Similar solids have the same shape and all their corresponding dimensions are proportional. The ratio of corresponding linear dimensions of two similar solids is the scale factor. Any two cubes are similar, as are any two spheres. So let's take a look at our first question. Problem number 1 asks, are the two cylinders similar? If so, what is the scale factor of the first figure to the second figure? So here we have two cylinders. Cylinders, as you'll recall, have two different measurements that are important. We have the radius and we have the height. So let's go ahead and compare radii and compare heights. So the first thing that we're going to look at is the radii. We have 6 and 6 becomes 5. And the heights, we go from 12 to 10. So if we wanted to compare these, we need to ask ourselves the question, is 6 to 5 the exact same thing as 12 to 10? And one potential way to check this is to cross multiply. So 5 times 12 gives us 60. And if we multiply 6 times 10, we get 60 as well. So we can see here, in fact, these two are similar cylinders. The scale factor of the first figure to the second figure is the most reduced version of this fraction, or 6 to 5. So when we were working in chapter 10, I told you that this would eventually come to fruition. We have two similar rectangular prisms, and they demonstrate something that's very important. If the scale factor of two similar solids is a to b, so in this case we can see we have 3 becoming 6, we have 1 that becomes 2, and we have 2 that becomes 4. So in each of these, 1 becomes 2. If we look at their surface areas, it's 22 to 88. Both of these numbers have a factor of 22, so 22 divided by 22 is 1. And 88 divided by 22 is 4. So we can see in the linear dimension, they have a scale factor of 1 to 2. But once we go to surface area, their ratio is 1 to 4. So we can see that their corresponding areas are in ratio of 1 squared to 2 squared. If we look at their volumes, we compare them, 6 to 48. Both of these share a common factor of 6, so this reduces to 1. 48 divided by 6 is 8. So the ratio of their volumes is 1 to 8. So you can see that this is 1 cubed and 2 cubed. Okay, so much like we did back when we were working with area, I would try to start by dealing with this in terms of volume as much as possible. So in other words, I would try to reduce the fraction 729 over 1,331 as much as possible before I converted it into scale factor. In this case, this fraction doesn't reduce any further. So the next thing that I have to do in order to get this into scale factor land, I have to take the cube root of both numbers. So I'm looking for a number that multiplied by itself 3 times gives 729. And again, if I follow the instructions for taking cube roots, I can find that that number is in fact 9. Taking the cube root of 1,331, the answer is 11. So check one last time, make sure that this fraction is reduced as much as possible. And the scale factor is in fact 9 to 11. Okay, so question 3 states that the lateral areas of two similar paint cans are 1,019 centimeters squared and 425 centimeters squared. The volume of the smaller can is 1,157 cubic centimeters. And we need to find the volume of the larger can. So the first thing that I would do is set up some kind of chart. I would track the smaller can and the larger can, and I would check them based on lateral area and volume. So the lateral area of two similar paint cans are 1,019 and 425. So the smaller of the two is 425, while the bigger one is 1,019. The volume of the smaller can is 1,157. And we want to know the volume of the larger can. So immediately the problem that I run into is lateral area is calculated based on square units, while volume is calculated based on cubed units. So the first thing that I would like to deal with is I'd like to have them in the same units. So I would convert all of these into base units. So I would take lateral area and convert it into scale factor. So I would have the square root of 425, and on bottom the square root of 1,019. As far as volumes are concerned, I have the cube root of x, and I have the cube root of 1,157. Now these are also in scale factor terms. Now that I have them all in scale factor, I can actually compare them as a proportion. So I have the square root of 425 divided by the square root of 1,019, and that's going to actually equal the cube root of 1,157 divided by the cube root of x. So now I can actually cross multiply. I have the square root of 1,019. I'm going to multiply that by the cube root of 1,157. And that's going to equal the cube root of x times the square root of 425. So here I'm trying to get the x all by itself, so I'm going to divide both sides by the square root of 425. So these now cancel. So let's go ahead and do some calculations here. Let's calculate the cube root of 1157. When I put that into my calculator, I get something that's close to 10.5. 10.49811. So I'm going to multiply that by the square root of 1,019. And so once I've done that, I have something around 335. 335.118352. I'm going to divide this by the square root of 425. So having done all these calculations very carefully, I get that the cube root of x is about 16.2556. Now in order to find the volume of the larger can, I just need to cube this. So the value of x, the original volume of the can, is somewhere in the neighborhood of 4,295 cubic centimeters. So as you can see, this ends up being a lot of calculator work. You have to be very careful with order of operations, the cube roots and square roots on the calculator. So one final note for this chapter. You can compare the capacities and weights of similar objects as well. The capacity of an object is the amount of fluid that it can hold. The capacities and weights of similar objects made of the same material are proportional to their volumes. Let's look at our final problem for chapter 11. A bottle that is 10 inches high holds 34 ounces of milk. The sandwich shop pictured is shaped like a milk bottle. To the nearest 1,000 ounces, how much milk could the building hold? So the first thing that we want to do is we want to calculate the scale factor. So we have 10 inches high for the bottle and 480 inches high for the sandwich shop. So reducing this fraction, we can see that the scale factor is 1 to 48. Now the scale factor doesn't tell us anything about capacity, but the volume does. So let's go ahead and cube both of these. So let's have 1 cubed and compare that to 48 cubed. So 1 times 1 times 1 is 1, while 48 cubed is 110,592. In other words, for every 1 ounce that the bottle holds, the sandwich shop will hold 110,592 ounces. So we want to set this up as a proportion. 1 over 110,592 is going to convert into 34 over some number x. So by cross multiplying, we have 1 times x equals x, and our answer is going to be 34 times 110,592. So x's true value is going to be 3,760,128. So to the nearest 1,000 ounces, we're going to round down. So this is going to hold about 3,760,000 ounces of milk. I guess that's only true if they don't open one of those windows. That concludes section 11.7, areas and volumes of similar solids. And that also concludes chapter 11. Thanks for your attention, and I'll see you guys soon.